Welcome to the Department of Energy National Lab Discovery Series webinar. I'm Hannah Farquhar, and I have the privilege of being your moderator today, hosting a wonderful team of speakers. I'm from Lawrence Livermore National Laboratory and coming to you from Livermore, California, as is everyone else you're going to hear today. We work at Lawrence Livermore National Laboratory, and it's one of DOE's 17 national laboratories. We apply science and technology to make the world a better place. We like to say here that we are science and technology on a mission. At LLNL, I work in our Innovation and Partnerships Office, where we are responsible for making our technology and innovation available to the private sector through technology transfer. And that's what we're here to seed and talk about today. So I'm very excited to share with you an LLNL technology, a software product called TAOS. It's an alloy optimization software platform. And we're very excited to show you the accomplishments of our researchers and then the opportunity for you to evaluate the software product. We'll share with you how you can do that later on in the presentation. So in the next half hour or so, you're going to hear from LLNL researcher Aurélien Perron. He is a key member of the team that has and is continually developing the TAOS software platform. Aurélien is currently a deputy group leader at LLNL. His research focuses on alloy design, thermodynamic modeling, and microstructure evolution. He's leading projects focusing on alloy optimization and software development, and that's what you're going to hear about today, and can't wait to get there. But once Aurélien is done with his presentation, and he shares all of the exciting details with you, my colleague Mary Cordero, formerly Holden Sanchez, will share with you LLNL's business model for making TAOS available to you. So Mary is a business development executive responsible for commercializing LLNL software portfolio here at Lawrence Livermore. So stay tuned at the end of Aurélien's presentation for information on that. Quickly, before we begin, I'd like to remind you that your microphones will be muted throughout the presentation. If you have any questions, please type them into the Q&A tool. We'll be monitoring the Q&A tool. It's either at the top or the bottom of your screen, depending on your system. And we will address your questions in a Q&A session at the end of the presentations. And we're going to do our best to get to as many questions as we can, because we know that you guys are going to be engaged and want to learn more about this TAOS software system, our tool that we're going to talk about today. And so enough of me, enough of this introduction. I'm now going to turn it over to Aurélien, who's going to tell you many more details about the TAOS software. So Aurélien, all yours.
Yes. Hi, everyone. I hope you can hear and see me okay. So I'm Aurélien from Lawrence Livermore, and I will be presenting the alloy optimization software, or TAOS. First, I would like to highlight the team behind the software, namely Nicolas Yuri, Brandon Boklund, Vincenzo Lordi, and myself. So to start, in a nutshell, TAOS has been developed to empower a broad spectrum of users to leverage computational design for rapid alloy development. So at the end of this webinar, if you are interested in the documentation or just knowing more about TAOS, please feel free to visit this web address or just to scan this QR code. So now you can wonder why initially we developed this tool at Livermore. So as of today, materials are really key limiters to many applications. So you can think about really like broad application, like nuclear. It can be fusion application or fission application. Material, we need like really high performance materials. You can also think about materials for high temperature application, like turbine blades, radiation resistance application for space, but also like more like developing materials resistant to degradation. And in that case, you can think about like corrosion. So really, there are like a lot of opportunities for new materials to solve these challenges. However, there are some bottlenecks. So first, there is a really long alloy development cycles for materials, and it involves a lot of experimental trials, so it is costly. So if you look at the picture on the bottom left, this is an example of like nickel superalloy developments. So if you, from like the initial development of nickel chromium alloys in the 1920s up to today, it took like 100 years to really optimize these alloys. And to really improve the properties, it's a combination of both like process optimization, so the manufacturing, but also the alloy design part. So what I call alloy design here is like the chemical composition of the alloy. So how do you fine tune the chemical composition of your alloy so that you can process it and obtain the properties you are looking for? So if you look at the chemistry of the alloy, you have like really a lot of options. So if you look now on the figure on the right side, that gives you an example. So if you have a design space, let's say like 5, 10, or 15 elements for your palette where you want to design a new alloy. If you look at the y-axis, the number of alloys you can generate just based on the combinatorics, clearly reach like untractable number really quickly. So what we really need is to like accelerate and reduce the cost from design to development of new alloys. So fortunately, we are not the only one trying to do this and tackle this problem. So there is a global solution with the arrival of like Industry 4.0 or the fourth industrial revolution with the digital transformation. And it goes with like really like great advancements in manufacturing technologies. You can think about additive manufacturing, for instance. So at Livermore, we developed within this context a new software tool to optimize alloys with like targeted properties, so really what you are like after under applied constraints. And here, when we talk about constraint, it can be constraint regarding like also materials properties, but also maybe you have like constraints on the supply chain. Maybe you cannot afford some of these elements. So that's what we're trying to include in the software to help the design. So this is what really TAOS is about. That's a powerful, easy to use R&D tool to accelerate the design to deployment cycle. So on this slide, you can see like a quick summary of TAOS. So on the left column here, really TAOS is like database and model agnostic. So you should be able to run TAOS on your laptop, either if you're using like a Mac or Windows system, it doesn't matter. Then you can use like CALPHAD databases or other sources. I will come back to that. You should be able to bring your own model. If you have like a proprietary model for your like custom your properties, you should be able to do that too. Once you have loaded, your materials models, you can use them to define your optimization problem. So you can be targeting some specific thermodynamic properties, mechanical properties, or any property that you can have like a model for. So you can do both like unconstrained and constrained optimization problem. And by the end of the day, you should be that like really quickly to be able to assess experimentally your material. So if you look at the micrographs on the bottom right of the slide, this is an example where we try to generate a columnar to equiax transition for some titanium alloys under selective laser melting condition. And we were successful, like so on the left side, that's the alloy before optimization. And on the right side, that's the alloy after optimization, when we had like a lot of like nucleation and equiax grains. So here is how like the interface is looking. So of course, it has like a graphical user interface for ease of use. And on the left side, on the left panel, that's where you will be loading your database and models. In the middle of the screen, that's where you can define your target function, your objective, but also input your constraints for your optimization. And on the right side, that's where you will see your optimization results and where you can also like do some post-processing of the results. So first, I would like to talk a little bit about CALPHAD database and models because TAOS by default includes some CALPHAD backend. So if you are not familiar with the CALPHAD method, it stands for calculation of phase diagrams, and you don't have to know a lot about it, but just to let you know, it's a collection of phase-based, so liquid, BCC, etc., other phases, models that enable you to rapidly predict thermodynamic properties in multi-component system. So how can you use it actually to design new alloys? So you can do some calculation to design new alloys. Let's say we targeted like heat treatment or service condition, Why? Because as function of like temperature or composition of your alloys, you can calculate what phases will form, their fraction, their constitution, but also the melting temperature of the alloy. So you can think about like if you want to do an LLNL treatment or solutionizing heat treatment, precipitation heat treatment, things like this, you can do that. You can also target alloys for like manufacturability or processing. So how do you do that? You can also calculate a lot of properties that are related to solidification. So at equilibrium or under non-equilibrium condition, you can calculate like partition coefficient that will give you an idea about the segregation of your alloys. Cracking susceptibility, so there are a lot of models to estimate if your alloy will crack or not during solidification. And what you can do also is go directly after some physical properties. Maybe you are interested in optimizing for like heat capacity of your system or a specific density or a coefficient of thermal expansion, things like this. So really the bottom line is that it's really an established method since the 70s, and it's really efficient. It's kind of really cheap to calculate these properties. So it's really useful for alloy design. So coming back to TAOS, I said that like we include as a backend CALPHAD database and software. So it directly integrates PyCalphad. So it's a thermodynamic engine to run CALPHAD calculation. And we also include some thermodynamic databases where you can run some example and test the software. So you can also have access to open databases in the literature. So TAOS is compatible with these open CALPHAD databases. And if you are interested in a third-party provider, TAOS is also compatible with the thermocalc databases through the TC Python interface. So now coming back to some example on how you can use the software. So here I will talk a little bit about the aluminum copper silicon system. So this is an example that you can find in the TAOS documentation. You don't have to be really familiar with like this, for instance, this Lucullus projection in the ternary system, but it's just to highlight what the software can do for you. So here, for instance, if you're interested in minimizing the liquidus of your system, that's the temperature at which your alloy, if you start from a high melting point, a high like your alloy is completely melted, if you decrease the temperature, when it would start to solidify. So you can see that for in this system, the minimum melting point is at like roughly 500 degrees C, and it corresponds to a eutectic system. So the liquid phase directly transforms into 3 solid phases. So it can be interesting for, let's say, some typical microstructure that will form and will rise to interesting properties. So this is one, but there is another eutectic in this system, much more on the copper side, that we will try to characterize. So now how are you going to do that in TAOS? So first, the first step is to import a database. So if you remember, that's the panel on the left side of the screen. So here, it's fairly natural, like every software, you browse, you can select your database or TDB format for CALPHAD, and it will load it automatically. So you can see that, for instance, we loaded like a database with like 3 elements, aluminum, copper, silicon. Then what you can do is you can set your active components. So because maybe you have a database with a lot of elements, but you want to refine your design space in only a few of them. In this example, we'll consider the 3 elements of aluminum, copper, and silicon. Another thing you can do, you can select or suspend some of the phases. For instance, if you have a system with metastable or stable phases, you can select to apply or suspend them, depending on what you are interested in doing. So you can do that. And finally, on this screen, what I would like to highlight is the load and save buttons, because you can really like load your projects with all your databases, your different target constraints, and just like reload it to accelerate your optimization loop. So now let's go to the middle panel when we're trying to set the objective. So in that specific example, we are interested in minimizing the melting point of the alloy. But you can see that you have like a lot of different options that are already like included in the software. So I won't go through all of them, but you can technically minimize or maximize any of these functions. So you can be interested in chemical composition. So here, for instance, if you want to do like, let's say, high entropy alloys or something like this, you can use a target as the number of elements. You can try to maximize the number of elements in your alloy. Regarding solidification, again, a lot of different factors regarding solidification range, can be interested in like nucleation, cracking indices, or melting temperature, as in this example. And on the right side, what you would qualify as like equilibrium calculation, so you can also constrain some phases to form at some temperature. So that can be interested if you are like specifically targeting like heat treatments, or if you have a specific like service condition in mind. So for instance, a little bit more detailed example on the left side on the chemical composition. Here I selected the composition summation. So I pick like copper and silicon in that example, but for your specific application, you might be interested in minimizing like costly elements or elements that you know will be critical or that really you want to minimize. So that can be the use of this function. Regarding solidification, if you are interested like maybe in casting, you have different like cracking indices that you can try to minimize. And if you don't really know what these indices are, you can always like hit like the help button. So it will give you like some details about what are these functions. And if you're really interested in going in more details, you can always look at the documentation. And finally, for manufacturability, you can also pick, in that example, the equilibrium phase summation. So you can select the phases that you would like to form at a given temperature. So here, one interesting feature is that you might know your temperature, your surface temperature. So if you're interested in some precipitate at a given temperature, you can do that. So that's like the absolute temperature. But if you don't really know that, you can always select the option of like the fraction of solidus. So you can always use also a relative temperature compared to one of the melting point of the alloy. So really, what TAOS is doing is you can do like alloy design really from like a green field if you are interested in exploring like really new alloy composition, but you can also basically improve on an existing alloy if you're interested in adding like a specific constraint or improve on a specific target. So in this example, going back to the objective, it's a simple one. So we just picked like melting temperature and we're trying to minimize the liquidus temperature. Then you just have to click the run button and you will have like here, for instance, the output of the optimization. So it will give you the alloy composition and the liquidus solidus temperature. And our objective was minimizing the liquidus. You can also, if you look at live, have an evolution of the optimization and it will track the different alloy composition that were tested. So if we go back to our initial example from the literature, we can see that we can indeed minimize the melting temperature in this alloy. So now to highlight another feature of the software, maybe in a world where you could not use a lot of aluminum, let's say because, I don't know, the powder is too reactive or it's become all of a sudden too expensive. And for your problem, maybe you cannot use more than 25 atomic percent of aluminum. So technically you cannot use the composition that are in this like shaded area. You are limited to this area. So how can you now minimize the liquidus in that composition space? So it's basically transforming your like unconstrained optimization problem. So we only had like one objective into a constrained optimization problem. So here we are going to add a constraint on the composition of the alloy. So I won't go back again through all the different features here that you can do, but know that all the functions that you can use for like objective, you can also use them for constraint. The main difference for the constraint here is that if you look at the composition, now you can play with the ranges. So in that example, we want to have like aluminum, these elements, between like 0 and a maximum of 25 atomic percent content. So that's what we selected. And then you can, again, run the optimization. You will have like the results, and you can double check with the literature that the results matches. So this was like, I would say, a fairly simple example to highlight how TAOS work. And now let's take another step with an example that's a little bit more complex. So if you take like nickel-based superalloys, so let's say you are interested in refining the composition of a nickel-based superalloy. So here I don't claim that's what we are going to do in this webinar, but it is to show you how you could use the software to do it. So let's say you are interested for a nickel superalloy, so in a nickel, aluminum, cobalt, niobium, molybdenum design space. And so what are you going after for a superalloy? So you want to have like an ordered phase at high temperature, so gamma prime, to give like strength to your alloy. But you also, because of your process, you want to minimize cracking. So what you want to do for that, you want to solidify your alloy through one phase, so mainly FCC at the end of solidification, and you want to have a narrow solidification range. So the state where the alloys has both like liquid and solid phases. So now how do you translate that optimization problem you have in mind in some like objective and target functions? So the first thing you want to do is to maximize your gamma prime amount at 750. Let's say that's your like service temperature you are targeting. You want to maximize strength at that temperature, you want to maximize that phase. Okay, you have your composition space. You want like mainly a nickel-based superalloy, and you can give room for the other elements to be in between like 0 and between like 30 and 50%. So that's the start of your optimization. Then you can add some constraints. You say, okay, I want my alloy to have at least 5 elements, because ideally I would like to combine solid solution and precipitation strengthening. So you can do that. Then your service temperature 750. So of course you want to have a lot of like gamma prime. So that's our like target, but we want to have at least 75 phase fraction of this phase. So that's a constraint during our optimization. We also want to keep at least 10% of the initial like FCC nickel phase. And overall, we want to have like a summation of these two phases, so the nickel initial matrix phase and the precipitates to be above 90%. And why we do that is to try to minimize the amount of detrimental phases or other phases that could form that you want to avoid. And finally, for the cracking, you can say, okay, I don't know the melting point of my alloy, so I don't know the absolute temperature, but I can say, okay, at 99% of the solidus, so relative temperature, I want my alloy to be like 95% FCC, so really close to be single phase. And I want my solidification range to be below 100 degrees C. So with that, you define your like optimization problem. So how does it translate into the GUI? So one thing I would like to highlight here, that's the compatibility, again, with third-party database providers. So here, like for instance, we loaded like TCHA5 from Thermocalc, and the optimization problem is defined in the middle. So here you can see that we want to maximize the L1-2 phase at 750C. So the goal here for the GUI is that like you can read your problem and modify it if needed. So you can expand here some of these like constraints or just reduce them. So here let's look at this one, the equilibrium phase fraction constraint. You can see that at 750, we pick to have like FCC, that's the disordered one, to be above 10%, the L12 precipitate to be above 75%. Below that, that's the phase summation that I was talking about. So the sum of both should be above 95%. And if you look at the bottom, the solidification range here, so we want it to be below 100 degrees C. So it's really easy to like save, reload your project, change your parameter, and redo the optimization. So this is the result of this optimization. So it takes, I think, between minutes and hours. I don't remember exactly, but that's fairly quick. So we match, so on the right side, I'm sorry, that's what we called a property diagram. So that's the evolution of the phases as function of temperature. So that has been plotted using the alloy composition that has been like designed by TAOS. So you can see that the solidification range, this is this small delta here, is below our 100 degrees C, so at 35 degrees C. At the end of solidification at the solidus, we are 100% FCC, so we matched that constraint, and we also matched the other constraints at 750C. Remember, we wanted at least 75% of this L12 phase, at least 10% of FCC. However, one thing that we were not happy about during this optimization is that like, oh, here you can see that at 1000 C or 1250K, all of a sudden you have like 100% of the compound. And you want to avoid that because it will crack and become brittle. So, but that's not an issue of TAOS, right? That's because we did not constrain properly our optimization problem. But that's super easy to fix. You just have to add the same constraint that we had like at 750 at 1000 C. And another thing that we did, we added also like a minimum composition for molybdenum because we really like to have like molybdenum in this L12 phase. So you can tweak your problem, re-optimize, and it worked like immediately. So now that we have like properly constrained our problem for our application, we see that the FCC phase, initial matrix phase, doesn't go to 0, and that you maintain the number of the amount of ordered phase that you were targeting. So that's really to show you how you can like quickly iterate on your optimization problem. Okay, so now the roadmap regarding TAO. So everything that I showed you is available in the, I would say, version 1 version of the software that has been released. It was mainly funded by the Critical Materials Institute and the Technology Commercialization Fund. So clearly that was really useful. And I have to say also that we have an ongoing project, technology maturation grants, where we are adding features to the software. And really our goal is to respond to the needs of like companies, academia, government, so that the software can be useful to a broad range of users. And so the 3 features, I will highlight some of them here that we are implementing. So one that is really nice is bring your own model. So you can bring your own property model if you're interested. Not being constrained by one target, but doing like bi-objective optimization. So you can not target 2 objectives and doing like post-processing analysis. So let's start with the bring your own model feature. So the GUI is slightly different for the V2, so the release is scheduled in October. So now you will be able to leverage your own model via a Python API. So how does it, did we do that? It's because you have like, for instance, a lot of model in the literature that you could leverage, or you can have your own proprietary model that you don't want to publish, but you would like to leverage for an alloy optimization. So for instance here, what I'm highlighting is like a recent paper from our group that published like a CALPHAD-based model for molar volumes. There are also papers in the literature, analytical model for yield strength of high entropy alloys, BCC ones, but also machine learning models where you can like estimate ductility of this class of materials. So this can be really interesting because, for instance, again, in terms of application, I don't claim here that we're going to design in this webinar a new material for fusion application, but this is an example where maybe you have some requirements for your material design to have like a density requirement or a coefficient of thermal expansion, so you can use that model. You might have some requirement on the yield strength, so mechanical property, but you want to also have like some requirement on the manufacturability. You don't want your alloy to be too brittle. So the goal here is to highlight that you can use now these features with TAOS to design your alloy. So how does it work? So here it's a crop, but like on the left side of the TAOS panel, you can go to the preferences and you can directly import Python scripts or Python packages directly for your model. So here you can see that we had like PyCalPhad, compatibility with TC Python, and the different model I was talking about for molar volume, yield strength, and ductility. So once you have done that, you can now load your model for your optimization. So this is what I did here. Sorry, I went a little bit fast, but like on the left side, I loaded all the different models. So like the CALPHAD database for phase stability, the database, for molar volumes from the literature, the yield strength, and the ductility one. And as you are progressively like loading this model, you will like populate this periodic table. So how does it work? Is that you can select the elements that are available in like all models. So I selected, for instance, here like 4 elements: titanium, vanadium, niobium, tungsten. Again, this is just an example. Could have selected more or less. And the elements that are here in red, it's elements that are considered by some models, but not all of them. So you cannot really use them for your optimization. So really the takeaway is that now you can mix and match different models. Now you define your optimization problem again. So here, the example, I decided to maximize the yield strength of the alloy at 800 C, so for a high temperature application, let's say, but I want to minimize maybe density. So that's my dual or bi-objective optimization, right? I want to maximize yield strength, but decrease density. And I have here some constraints. So I want my alloy to be single phase BCC at 800 C. I want to have like at least 4 elements in my alloy. So I really want to stay in this 4 elements design space. And here regarding ductility, this is a ductility parameter model. So that's the machine learning model. I want this value to be at least above 3 because we think it's good for manufacturing based on experience. So after, you can run your optimization and you can see that even within like a 4 element space, the optimization went really quick. It takes like less than 2 minutes, honestly. And it generates a Pareto front. So what it is, because now you have like 2 targets, right? So you have a trade-off between your objectives. So we have density. Remember, we try to minimize density of the alloy, and we want to maximize yield strength on the x-axis. And so the red points here are your optimal or undominated solution. So you cannot see it here because it's a screenshot, but when you go over the points, it will tell you what composition and the properties of these alloys. But what you can also do is like do like a more like post optimization analysis. So when you click on that button, you can plot again here the same Pareto fronts, so density versus yield strength, but you can plot different version. And the orange points that you see here is the Pareto front. And the main difference between the black and the gray symbol is that the black symbols corresponds to the constraint optimization. So that's between quotes where your solutions are fully satisfied. That's your problem. And the gray one is the unconstrained optimization. So if you are really interested in analyzing like in more in-depth all these results, you can always go to the table content where you can like see as function of composition, you have the different properties that you calculated, and you can basically extract only the solution on the Pareto fronts or all the calculated point, export them as a CSV file, and open them with Excel and do any kind of like analysis you want to do with. Another thing that's nice to show, I think, is the relationship between the alloy composition and the properties. So here the yield strength is plotted. And if you follow, for instance, maximizing yield strength, the green line, you will see that you will have a tendency to maximize the tungsten contents while minimizing vanadium and titanium. But you can also add all the other properties that you calculated to see this kind of relationship. So here I added like density because we wanted to minimize density. And you can see that for high density, yes, high yield strength, high tungsten constant. But if you want to minimize density, you can sort, by density. So I went a little bit fast, but like here you can sort the colors of your parallel plot. So here I sorted by density. So we were interested in minimizing like density. You can see that, of course, it will correspond to higher titanium content and low tungsten. But this is really to show you how you can analyze your data also within TAOS. So in summary, TAOS automates the search for optimal alloy design from greenfield design to fine-tuning existing alloy. The GUI is really easy to use. And something I would like to mention is that it's an offline tool. You don't have to be like connected. You can have like almost completely like air-gapped computer and use it. It's for like commercial, academic, and government use. You don't have to be a specialist in computer science to use it. And really, our goal is to respond to people's needs. So we are really open like for contact and discussion. We also have an email address if you have some question or some help. This is the taoshelp.gov. And with that, I think we'll transition to Mari, who will talk about the business model.
Thanks, Aurélien. So TAOS is currently utilized by the US government as well as academic institutions and industry partners around the world. We're offering a free 3-month evaluation license for the demo version of TAOS. And the complete version is also available for licensing on a per seat basis. Licenses are valid for 5 years with a one-time payment. And so we have licenses for academic, commercial, and for government use. And on the website, you can click order now to request a quote for the full version. TAOS is licensed directly through LLNL software store at softwarelicensing.llnl.gov. And the entire licensing process, including the credit card payments, is managed through the store, and software is delivered electronically.
Wonderful. Thank you so much, Aurélien and Mary. Really appreciate that overview of the software tool. We're already seeing some questions come in, but I want to remind our audience we're now going to open up the Q&A session. And so please enter your questions into the Q&A tool as we proceed. We're going to try to answer as many questions as we can. I'm gonna start with one just to kind of set a further stage, Aurélien, if you don't mind. What was the impetus for the creation of TAOS? When did this start, and what led to its development?
Yeah, thanks Anna for the question. So I would say it started with like internal needs more than 10 years ago now, but like we were interested in designing, let's say, like new magnets with less like critical rare earth elements. We were interested in designing new aluminum cerium based alloys and matching the need of some of our like industry partners for solidification ranges. So that's how we started, and we saw that the tool could be useful for the broader community. And I would say that between quotes, we are lucky to secure some funds to generate this graphical user interface that make it like really easy to use, and that's where we are like today. So yeah.
Awesome, wonderful, thank you. So I'm going to jump into some of the attendees' questions, and they seem to be all for you, Aurélien. So and I will point out that we have 2 other developers here on the webinar to help us answer some of your questions. Brandon Bachland and Nicholas Fury. They're also developers of TAOS, and they'll be jumping in for anything we need. So again, any technical questions, we got you covered. So please put them in the Q&A. So the first question we have is how can you check if the alloy is synthesizable?
Okay. I can start with that one, and yes, again, Nick, Brandon, feel free to jump in if you feel like I missed a point. So, so this is where like both, I think, knowledge from the manufacturer or like metallurgist in general and the tool are really like synergistic. So, for instance, I talked a lot about like minimizing maybe freezing range or like cracking indices for casting application or AM application. So this is something the software can do super easily. Another thing I mentioned is like ductility models for some of the refractory alloys, because some of them, yes, like you can have a good yield strength, but it will shatter immediately as soon as you make it. So that's where having this ductility model we thought was useful to demonstrate. So this is really like how you define your optimization problem. So TAOS is really agnostic I would say in the materials problem it can solve. And in terms of manufacturability, we have at least like these 2 parameters in place. But after, if you have like other metrics in mind that could be used as constraints or target, it can be implemented through the bring your own module of TAOS, or contact us. I don't know if it's answer entirely the question, or if Nick or Brandon, you have more to say about it.
Yeah. Sounds good. We'll move on to the next one in a kind of similar vein. Do you consider alloy impurities and their impact on any variation melting point?
Yes, that's short answer. Okay, so so in that case, so for the melting points specifically, or the phase stability, it will rely on the CALPHAD backend, at least if you are using a CALPHAD database for this calculation. You might be using like a machine learning model to estimate melting point of the alloy. So in any case, it depends on how the models have been developed. So in the view of the CALPHAD models, if your impurities are included in the CALPHAD database, or in the CALPHAD model, you will be able to consider it for the melting point. And same, if you have like a more analytical or ML type model, if during the training these impurities have been included, it will be included by default. If not, yes, no, there is no magic there. I hope it helps.
Thank you, Aurélien. And then we have a couple of questions in this range about, do you have to purchase the databases separately from Thermocalc?
Yes. So, okay. So the difference, or maybe I can go back to this specific slide actually. I will try to go as quick as I can without jumping over. Okay. So that's what this slide was about. So if you are interested in CALPHAD databases, so there are different sources in the literature for open one. So what I mean by open one is that yes, you can download them and use them directly with TAOS. So CALPHAD Journal is a really good source for that. Google Scholar is a really good source for that. If you have more questions, you can contact us, of course. If you are interested in third-party databases, Thermocalc ones are a really good example because they are like compatible with TAOS, but we don't provide them. That's a third-party provider, so we'll have like to contact Thermocalc, buy your databases, but when you install TAOS, it will automatically detect that you have them if you have the TCPython interface on top of it.
Very good. Very good. Yes. Very flexible when it comes to your databases and the data you can use, right?
Yes.
Okay. And here we're getting really technical, so you're gonna have to excuse my my pronunciation of these. But does TAOS calculate the solidification ranges based on the Shield-Gulliver model, or is it just the solidification range from equilibrium, liquidus, solidus at a fixed composition?
Yes, okay. So you can do it all. Yes, okay. So if you see the solidification range, so it's behind this slide, but that's similar to the melting temperature. You can see that here, for instance, for the melting point in that example, we minimize the liquidus, but we could have taken the solidus at equilibrium or the solidus using the Shield-Gulliver assumption. So both of them are included as calculator in TAOS, so you can do both.
Very good. And again, same vein, I'm just going to keep reading. These are all for you. Very impressive. Does the software account for transient or time-dependent mechanisms that may affect the evolution of the microstructure and properties, like grain growth or phase transformation under a variable temperature heat treatment that lasts a certain user-defined time? Is there a way for the user to manually account for such transients?
Yes, yes, I would say yes, really good question. Complex question. Okay, so one thing we can do is that if you know, that's kind of a little bit of like this objective of like suspending phases. Like let's say if you want to suspend like graphite, for instance, or a phase like this that you know you won't see under equilibrium condition, you can do that here and tweak your optimization problem to consider stability versus metastability. Now, if you are talking about really like more kinetics in terms of like modeling diffusion and precipitation, okay, this is something as of today that is not included in this version of TAOS. But that's a really good insight. Thanks for the question. I don't know if Brandon, Nick, you want to add to that or no?
Nick, I got one.
Yeah.
So in the version 2, when we introduced like the custom like bring your own model feature, you were ideally be able to make a custom model that like computes like these kinetic like terms that you could import into the TAOS to optimize.
Okay. Yeah, that's a good point. Thank you, Nick.
I guess that may answer this next question as well about does TAOS incorporate kinetics? Are there plans to in the future?
Yes, I think overall it addresses that one.
Okay. And then how many new alloys have you created with this tool? And how do you verify experimentally a candidate material?
Yeah. So one example I can give is like we worked a lot in the past on new aluminum cerium alloys that won R&D 100 award for the development of these alloys. So at the time we didn't have the GUI, but we used the backend that I talked about to design this alloy. So that was a successful story. And we have like other applications that are like internal to the lab. So yes. But just maybe to finalize on that question, so all the alloys that we usually design, we have like an experimental team or partner that is like working with us because that's their objective. Our objective or the objective of TAOS is really not design alloy like for fun. You can do it if you want, right? But like really the goal of TAOS is to be installed on a computer, ideally like in a small or large business research environment, anyone that is interested in actually making alloys or like producing powder, this kind of application. So really the end goal is to have a real material. It's just not to do that for fun.
Okay, perfect. Is TAOS designed for combining molten metals or combining 3D powder metals for sintering?
Can you repeat the question a little bit slower, and I'm sorry?
Yeah. Is the software designed for combining molten metal or combining 3D powder metal for sintering?
Okay. So if I understood the question correctly, so it depends maybe on your target. So if you are interested in really targeting a property for the end product, so let's say if you are using like additive manufacturing, you are mixing like elemental or maybe premixed powders, what in that case the CALPHAD calculation will do, it will tell you what's the property of the final composition. So it will help you optimize the final alloy composition. It will not help you telling you if you should mix like more aluminum with, I don't know, cerium or like silicon, whatever you name it, like has like elemental powder or premixed powder. That's the final state. So, and for sintering, even if it's like, yes, more solid state, again, what you are going to predict is the final state, thermodynamic final state. Yes. I don't know, Brandon, Nick, any more insight? Did I butcher that one or?
I doubt that. Okay. We'll move on, and I'm going to read this next question. I think it's for me or Mary to answer, but do you offer consultancy for alloy development as well, like having the ability to call your expert?
Okay, so I think that one is not for me, all right?
Yeah. No,
Okay.
I can take
Okay,
this one and
sorry.
say, yeah, Lawrence Livermore National Laboratory is an FFRDC, our federally funded research and development center, and in that way, we can do contracted research for outside entities, and so it's similar to a consultancy, but not quite. And there are some we do this quite often where Livermore National Lab scientists do research for private sector entities, for other government entities, and so it is possible on some predefined contractual mechanisms that we have. So please reach out if that's of interest, and I can share more details or put you in touch with someone who can share more details about those mechanisms. So. Okay, we'll move on. I see we only have a few minutes left, but I'm going to try to get to as many as possible. So, is there any way to apply constraints to optimize the reactive oxidation properties of the alloys?
Okay. If you have a model or a database that maybe can calculate the enthalpy of oxidation, maybe that's something you can do. I don't want to speak too fast. That's an interesting problem that I haven't thought about, honestly, in the past. But I think we can. Okay, so the short answer, general answer would be trying to think about this in terms of an optimization problem. So what are really the property you are targeting and or which constraint? And if we can calculate some of them, the short answer is yes. And how to do it might be more or less complex, but yes, sorry, that's a general answer, but that's, again, feel free to contact me if I would be happy to think about it.
Love these new problems brought to the software and brought to you guys. I loving our audience questions, I must say. Do you have an example of the time savings enabled by the optimization algorithm implemented in TAOS when compared to brute force screening methods?
Oh, that's a good one. Okay, so I didn't do the math for the 4-element system or higher, but yes, there is clearly would be like, if you look at this, it was, sorry, in the introduction, at the number of like, the combinatorics I was talking about really early on. Yes, on this plot, right? So if you look at the 4-element system, maybe you can try to brute force it, right? It also depends. So this answer is several-fold because it depends on the complexity of your model. If you are only talking about a CALPHAD model that's like fairly cheap, analytical model, super cheap, yes, you can brute force probably a lot of things in the 4-5 elements. If you are like starting to have like a bring your own model where you couple to something that's much more like proprietary, like expansive model to run, that's where the optimization strategy is really like gaining traction, right? Because all of a sudden you cannot do 10,000 calculation. So you might be limited to do like 100 iterations, and that's it, or even less. So I don't have, I would say, it depends on the scale of your problem, a concrete number, but that's also a good point for next time. But yeah, I think it drastically speed up because like a lot of the simulation are not that cheap. And if you are expanding your palette of elements, it's become intractable to brute force anything anyway. So yeah.
Very good. Thank you. Okay, we're going to keep going. I'm going to try to do 2 or 3 more, and then we'll do a wrap up. But are the databases limited to certain elements, or can we calculate the manufacturability for any combinations in the whole periodic table?
Okay, so so it becomes a CALPHAD centric question. So it depends on the database. So some of the databases have like between like I would say 5 and let's say 15 elements. So you can look at the database provider, you can look in the literature. It will be like directly linked to the database you are using. So as of today, there is no database that covers the entire periodic table. But if you are more interested in like high entropy alloys or nickel superalloys, titanium alloy, aluminum alloys, steels, you name it, different databases, specialty ones have been developed for these applications. So it also depends on your application.
Very good. And in a similar vein, if a material does not have data in the temperature range of interest in the database used, what will TAOS do? Extrapolate, not compute, etc.
Oh, okay. Oh, okay. So for this one, Nick, can you help me with that one?
I think as also Brandon mentioned was this will be dependent on both like the database, the models, and the software, based off like what will the database or the software do if you reach that temperature range. But the other thing too, since the temperature range is kind of user defined, you could probably just limit the temperature based off like where you know what the database is modeled against.
Okay. Yeah, you can play some safeguards that way. Yeah.
Very good. Okay, I'm going to say this is the last question, and could you please elaborate on how to import material properties such as molar volume and yield strength? I noticed they are provided in the TDB format.
Yes. Nick, sorry again, because
Yeah, I guess I could answer that one. Yeah, the way it works right now is that basically there would be a package and a Python package that's kind of imported in TAOS, and you were kind of subclass like this model. And in the model, you would kind of implement a function that would just say like, given your composition, temperature, and pressure, output a property. And that's how most of these like models are implemented right now. So the molar volume is that we have some TDB file that we import in to like our Python script that computes just the molar volume based off your composition, temperature, and pressure. And that's how it's being computed. But it's not limited to the TDB format. So one example is like when we had our ductility parameter, that's using like a machine learning model and doesn't require a database to be loaded. But in the end, it's the same thing where all it is just boils down to as long as you can compute your property based off like your composition, temperature, and pressure, then you can implement it as that like sort of function and import it in. But once that version 2 come out, we'll probably have in the documentation how you'll be able to implement like these custom properties.
Okay. Thank you, guys. Thank you, Nick. Thank you, Aurélien. I have thoroughly enjoyed this. I love hearing about this product, and I can't wait to see the impact it has in alloy optimization. And I'm going to say Mary is here for you if you have more questions about access to the software. So make sure you reach out, make sure you check out the demo version. And so if you have any further questions, feel free to send them to us, to any technical questions or business type questions for Mary. And I'm going to close it for today since we're at time. And I want to thank all of you for joining us, especially Aurélien, Mary, Brandon, and Nick. Thank you so much for sharing your product with us. And I want to make sure I thank the Department of Energy's Office of Technology Commercialization for providing this platform for us to share TAOS with you. We very much appreciate it, and we look forward to working with many of you in the future. And I want to thank all of you, all of our audience, for your time and especially your engagement. This has been really amazing to see everyone so engaged in this, and look for more announcements of more webinars in this series. There's lots of technology out there at all of the national labs. And so thank you and have a wonderful rest of your day.